Okay, first off, new angle, yeah. And also, you should have read the title. We're going to be talking about complex numbers and where the polar coordinates come from and where Euler's famous equation or identity comes up. Is nothing like the basic stuff where you multiply by conjugates or like stuff like that, where you just learn about I in general. This is about where, like, I would say Euler, I think it was mainly him, expanded the complex realm to not just include solutions for quadratics that didn't have any solutions, but for a whole host of things, including stuff from calculus, mainly calculus, at least that I know of. But like, here we go. So let's start with e to the x, and you'll see why. Right? When we're talking about e to the x, we have a Taylor series for this. This Taylor series is going to be equal to, whoa, from n equals 0 to 1 of, now 1, ooh, infinity, ooh, that calculus did hit me hard today, I'm sorry, x to the n over n factorial, right? This is your Taylor series for e to the x. You should know this if you're taking Calc 2, or you should be knowing this since it's the AP Calc exam. Everyone should know this. This is basic stuff. So here's the fun begins. Here's where the fun begins. Let's let x equal to a new variable, I theta. And you'll see why theta, but for now, just think of it as another dummy variable, right? And I is your imaginary constant. So let's expand this Taylor series. So e to the I theta will be equal to, okay, so first off we have a 0, so that starts as 1. Oh, actually, I don't know if it's going to be minus, but we'll see. When you're talking about when n equals 1, we have I theta to the 1 over 1 factorial, right? So let's just say that plus I theta. I'm going to write down the 1 factorial, then write down 0 factorial, so we have some sort of consistency to the first, so we don't like get confused. So now let's do n equals 2, right? N equals 2, I squared is negative 1, so we actually don't have a plus here. We have a minus theta divided by 2 factorial, theta squared in fact, because we're squaring everything now. Now we're going to have n equals 3, I is going to be I cubed is negative I, and then we have negative I theta cubed over 3 factorial. So we have a minus again, I theta cubed over 3 factorial. Let's keep on going. I to the 4th is 1. Theta to the 4th is theta to the 4th. 4 factorial is 4 factorial, so that's going to be plus theta to the 4th over 4 factorial. Now we can go to the 5th one too, because why not? But I to the 5th is, again, I, because it repeats every 4 powers, right? And we're going to have something similar to this thing right here. So plus I theta to the 5th over 5 factorial, and so on, so on, so on, so on, so on. Now, this is begging me to do something, which is group all the I terms and group all the non-I terms into a separate infinite polynomial. And I think that's going to pay off well for us. So let's do that. Okay. One thing I will say is that there's an I. So let's factor out that I. We don't have to get rid of it. So I'm going to do this real quick. Now, this should be familiar to some of you, most of you, in fact, all of you, or at least if you haven't taken it yet, that's fine, but this should be familiar to most of you. What Taylor series is this? This is, in fact, cosine of theta. This is a Taylor series for cosine, so let's write that down. Let's write that I plus I down, since we factored that out. This is what? This is sine theta. How cool. So now we have a neat little identity for us to exploit in the complex realm using Taylor series. E to the I theta equals cosine theta plus I sine theta. And now let's do some observations with this particular formula to see if we can expand the complex realm right about now. Okay, so one thing we're going to notice is that this side of the identity resembles the standard complex form, the standard form of complex numbers, which is a plus bi, right? So since this resembles it so much, maybe we can like associate the cosine of theta with the a term and the sine of theta with the b term. And we can find set theta, whatever theta is, by dividing sine and by setting a ratio and saying that sine of this theta divided by this cosine of this theta has to equal b over a, and this is tangent. Obviously we're going to take the inverse tangent of both sides, and the inverse tangent of b over a equals theta. Maybe from here, looking at this, we can find another way to represent complex numbers in a different form. But there's an issue that we may arise by doing this. B over a can be represented in an infinite amount of ways, right? It's a rational number. 1 over 2, 2 over 4, 3 over 6, so on, so on, so on. But 3 plus 6i or 2 plus 4i is not the same complex number. They're two different complex numbers. So one thing we can do is, let's do this. Let's take a leap of faith with me. Let's multiply by an arbitrary constant r by the entire thing. So we're gonna get this. Right? You're gonna have this when you multiply it out, and look, r cosine theta and r sine theta. If you take in geometry, you would know that this is your base. This not basic. This looks very similar to your standard right triangle trigonometry, right? R sine theta is if there's a hypotenuse r and an angle theta. This side is r sine theta. Likewise, this side is r cosine theta. That's just standard trigonometry that you learned in your geometry class in high school, right? Now, this also rings a bell a lot because it reminds me on Cartesian rectangular coordinates versus Cartesian polar coordinates, right? When you have on the xy graph, you have a point here. You can represent this in two ways, using the radius and the angle, or you can use it the cookie cutter way by using y direction and x direction. To relate these two, you relate it in the same way of r cosine theta and r sine theta. So since this is reminding me of something, maybe I can form a similar Cartesian plane but different using a and b, right, as a form of x and y. Let's do that. Right? With 0 over here, 1, right? Because this is 0, right? If x is 0, no, y, this one is 0, right? Not moving up any, we're just moving to the side. This is 1, 2, 3, right? Likewise, this would be I, 2i, right? Because this is your y direction, this is your x direction. So this is your moving up and moving to the right. So since we found out a way to relate this using polar coordinates now, we may have found a way to do that. 2 plus I, this point right here, which is equal to 2 plus I, right, can be represented, since we know that this I, the coefficient of this I, which is 1, can be written as r sine theta, and the coefficient of the constant term, which is just 2, can be written as r cosine theta. if you find such an r, right, by using Pythagorean theorem, because we have the x and y coordinate now, and a theta, which we can use using inverse tangent, look, we have another way to represent complex numbers, aka we have discovered a polar form. So let's do this one real quick, right? So this is going to be 2 squared plus 1 squared. We're going to square root that. That's your r, which is 4 plus 1, 5. And your theta is going to be the inverse tangent, right? And then we're going to have b over a, which is 1 over 2, inverse tangent of 1/2. Kind of slow today. I can't really think that quickly on what the inverse tangent of 1/2 is. I don't think it's any special ones, but either way, whatever this number is, we can put this into the E format, since we know that this can correspond to this and this corresponds to that. Wait, no, this is the angle, right? But you get the point. This, since this is the radius, we can say that 2 plus I has to equal the square root of 5 times e to the I, and your theta is the inverse tangent of 1/2. Have a look. We have another way to represent complex numbers in a polar form. So now let's look at the polar form of -1. Why? Because we're going to prove the most beautiful identity in mathematics, which is Euler's identity, e to the I pi plus 1 equals 0. And we're going to prove it right now using polar coordinates. So to do that, let's think about the polar form of -1. And let's write that in the complex form too. Meaning, let's write this as -1 plus 0 I. And this will be equal to its polar form, which is the radius, which is from 0, obviously the origin. Radius is 1, because you're taking one step to this way. I hate my left and right. Taking one step. So the radius is 1. So we have 1 times e to the I. What is theta though? They're in radians, right? Because we're talking about that Taylor series was meant for radians, not degrees. This in radians is obviously pi radians. Pi radians is looking familiar, right? So we can say that -1 equals e to the I pi. Let's do one fancy little small step. Add 1 on both sides. We get that e to the I pi plus 1 equals 0. Beautiful mathematical equation. It's just -1 plus 1 equals 0 in a polar form. Has all the 5 fundamental constants, and these are 5 most important ones. We don't talk about the golden ratio. That one is low-key special in some way. But the 5 most important ones are here, and then one beautiful identity where they relate to each other. So, yeah.